before I start, I must make a little disclaimer, which is that even though I'm obviously interested in functional programming research, what normally pays my bills is writing music software in C++. Sorry. But the truth is that I think that the systems programming community is also interested in functional programming, and we can see this by the evolution of languages like C++, but also the latest proposals like Rust, which really try to incorporate more and more the functional programming paradigm. And this is good, not only because these developers get to use more functional programming tools, techniques, and architectures, but because these languages sit often at the core also of interpreted languages whose runtimes are implemented in C or C++, and by implementing often, let's say, a functional data structure in C++, we can surface it to higher languages like Python, let's say. So I started this research with the question, can we implement functional data structures in a systems programming language? Because functional data structures are particularly tricky here. Like, these languages don't often offer memory models that are particularly good for implementing this. And to make it more concrete, I chose to implement persistent vectors, because vectors are kind of the bread and butter of the C++ developers. So if you manage to solve this, you solve this problem for them. And I chose C++ maybe because it's my professional mother tongue, and to annoy the audience here a little bit. So to give some background, what do you do if you want to implement a persistent vector? Well, ideally what you want is to have a contiguous array of memory. But it doesn't work very well in a functional or in an immutable setting, because if you want to update the vector, you need to copy all the data. So what you can do is to compromise and split this data into chunks. Now you have chunks that you need to assemble somehow, and you can recursively assemble them in vectors and split them until you get this very regular data structure, which is a tree that contains the data at the leaves and some inner nodes, where the data structure is characterized by this constant m, which is the number of elements we put in every of these blocks. And it's important, at least for performance reasons, to keep this m a power of 2 to be. And even though in the pictures here I show this in blocks of 4 elements, in practice we normally use blocks of 32 elements. And what this means is that actually you can have a vector that contains every possible 32-bit integer with only 7 levels deep. And what this means is that in practice, for big vectors, the other factors like the working set size versus the cache size are much more important to your performance than the depth of the tree. That's why a lot of the operations in this data structure that are actually logarithmic are often said to be effectively constant. So if we want to search for an element here, we can just split the index into chunks of b bits and address it more or less directly by traversing down the tree. If we want to update it, we copy the chunk in which the element is stored, and then of course we need to copy all the tree up to the element we wanted to have. So of course we need to do some copy for the update, but it's not so much. There is a big amount of structural sharing. This is an important property for us. Now, there is a problem still, which is that what happens if I want to concatenate 2 vectors? It will seem, since this is a tree, that we could do so in logarithmic time. But the tree is too regular, right? We have this little gap here in this picture at the rightmost side that we need to fill somehow with an element of the second vector. So as we concatenate, we will end up doing it in linear time to the second vector, to the size of the second vector. But it was published a few years ago and actually presented in this conference that you can actually achieve a logarithmic concatenation if you relax the structure a little bit and you allow some nodes, some inner nodes, to contain the sizes of their subtrees. In this way, the subtrees can contain sometimes less elements than they would otherwise in the perfectly regular structure, and this allows you to define a concatenation algorithm that preserves actually the bounds of the tree, of the depth of the tree, while still operating in logarithmic time. This is called the relaxed Radix balanced tree. And this is now a confluently persistent data structure because it's able to merge 2 trees into one in sublinear time. So we have now this data structure that has effective O1, random access, update, pushback, and slicing. And more like really logarithmic here, concatenation, insertion, and push from, which is great, right? Like this is like effectively constant for everything that you will expect effectively constant in a traditional vector, but you also get all these goodies like confluent concatenation and all this stuff. So this is the data structure I wanted to implement, and this is where my contributions start. The first problem we see here is that I've been drawing the pictures like this, but when implemented in most functional languages, and this data structure is actually very popular in JVM-based languages like Clojure and Scala, the picture looks more like this, where every element is actually boxed. It lives in its own memory block. And if I show this picture to a C++ developer, they would be the ones throwing the tomatoes at me. So ideally, I will want to instead store the elements at the leaf directly. And we could do so, but now we have a problem. What if our elements are big? If my elements are big, now my leaves grow, and I lose the ability to reason or kind of this nice balancing that ensured the fast updates. Now it's no longer true. Now the updates actually become unreasonably slow. But what we can do to solve this is simply change the amount of elements that we store at the leaves. So if every element is as big as a pointer, we just store them directly in the leaf using the same branching factor. But if my elements are bigger, like in this picture, I simply store less elements in the leaf nodes. Likewise, actually, by doing this, if my elements are smaller, I can store more elements in the leaves and often get smaller trees. So this is what I call an embedding Radix balanced tree, which can also be extended to the relaxed version, which is characterized not by one constant m, but by two, one for the inner nodes and another one for the leaf nodes. I show in the paper how the different algorithms can be updated to this new structure. It's almost trivial if you think about it, but the important thing is that we should compute at compile time, and this is something that we can do in C++, what the size for, or what the branching factor for the leaf nodes should be, which we chose to be as many as we can fit in an inner node. So another thing that we observed when trying to implement this data structure is that actually there is a significant amount of metadata that actually sometimes is added by the language, right? Because the fact that you have two different kinds of nodes means that you have type tags, you also have an array, and this array might have some information about the size of the array. But we found out that actually a lot of this metadata was superficial for the algorithm, and the structure is so regular, at least for regular subtrees, that you don't need it. Iteration becomes a bit more complicated, but we propose this technique called position-based navigation or traversal that allow us to describe the algorithms on the data structure in a simple way still. But the big question here is, what do we do with memory management? Because these functional languages don't, these system languages very often, I mean, the reason we use them is because they don't have a garbage collector. So there are different things you can do. You can plug in a conservative garbage collector, like libgc, Bond's garbage collector, or you could otherwise use reference counting, which is the favorite garbage collection strategy for C++ developers. Even further, if you want to embed the data structure in, let's say, the Python interpreter or some other interpreter, this interpreter is probably going to give you some way to allocate memory and probably a garbage collection strategy. So we use policy-based design to factor out all the important aspects of the data structure that are affected by memory allocations, or the memory allocation strategy. And what policy-based design does is that it allows you to factor out aspects of the implementation without introducing a performance cost. Because of the way C++ templates work, everything is monomorphized at compile time, so it's instantiated and it can still inline things. And our benchmarks show that this abstraction didn't add any cost, actually. So the user can choose different policies, as we saw. And what's interesting is this transients policy, actually. And I'm going to talk a little bit more about what this transients thing is. Let's look at this piece of code. This function inserts every integer between first and last into the vector v and returns a new version of the vector with the elements in it. This vector type here is not the standard C++ vector, but my immutable vector. So this function works, but there is a problem, which is that inside the inner loop, we are creating a new version of the vector in every iteration just to forget it in the next iteration. So we're kind of allocating a lot of memory because we saw we still needed to copy some nodes just for nothing. Ideally, we will want to do that in place. So we use a technique proposed by Closure, which translated into C++ will look like this. You get a transient version of the vector in the beginning, and now you can use a mutable API in the scope of this transaction. At the end of it, you say persistent, and now you get a snapshot of this. So with this API, we can still respect the immutability of the input and the output, right? This is what we are interested in. But we consider everything that happens inside a transaction, and we can use this more optimized way of updating and building the vector for extra speed. Now, how does this work? Well, if you're using an automatic garbage collection strategy, you have to use, or you can use at least, the algorithm that Closure implements, which we provide as a policy, where at the beginning of the transient, you generate an identifier for your transient that we represent here with this sharp symbol. Now, when you want to update the tree, let's say we want to update this tree on the right, you look if the nodes that you need to touch are tagged with this identifier. In this case, they are not. So we need to make a copy of them and tag them. Once we do this, we can simply insert in place in the subsequent calls, which is great. But what happens if we're using reference counting? Well, if we're using reference counting, we always have information available about the ownership of the nodes, right? We always know what the amount of aliasing is in every node. So it could be that the situation at the beginning of this function is like this. The root has two references, one probably the one in this function, another one in the color, and the other nodes are just referenced here. So we can use this information to know that we need to copy the rightmost side of the tree, and once we do that, we can now do the updates in place. So the effect will be very similar as done with the Closure strategy. And these two strategies can now be combined with policies. This is one of the things you can see the details in the paper. There's something more interesting that happens here, though. There is one feature in C++ which allows you to distinguish between anonymous values and named values. This is what's called move semantics. So the idea here is that I have this function that calls pushback 3 times. The first time it does so in a named value, but the 2 times it does so in the result from the previous function, which doesn't have a name, it's a temporary. So in C++, you can use ad hoc polymorphism to implement in a different way the function for these 2 cases. And what we find out is that if you're using reference counting, an anonymous value is a transient. Because when you're saying this value is anonymous, you're promising, of course, that this doesn't have any aliases, so you just have to look at the actual aliasing in the nodes to see if you can update in place, and very often you can. Now in C++ you can do one thing even further, which is not particularly beautiful, but it kind of works in practice, which is that you can move a named value. And in this case, you're kind of casting it into an anonymous value. It's a way for the programmer to promise that this value is not used anymore, which is the case in this function. I should say objects, actually. It's about the objects what the move semantics are talking about. So the object, this local object, V, is not used anymore, so I can move it, and now actually the transient, and you could say faster version, is going to use everywhere. And once we have this, actually, transients compose, which is something that they don't do when you're using the traditional transient strategy, because I can call say hi, and with the result of say hi, and there is going to be any superfluous allocation in any of the 2 calls. Now, of course, I use move semantics from C++ here, but I hope this inspired some of the people that are developing like proper type systems and linear type systems, where you can maybe like just remove the move here and do it automatically, right? Because this is like a static property. And if you do so, you could say you're kind of turning persistence into a dynamic property of the system, right? You don't have as a developer to choose, oh, I'm going to use the persistent nice functional API or the mutable API from the transient. I just use the persistent looking one all the time, And it's just the actual amount of persistence that there is in the system at runtime that will determine the performance of it. So the other work we did on transients is related to concatenation. Because concatenation is tricky, right? We're concatenating two vectors, and that's why previous work on this didn't try to address transients for this. Because as we have two vectors, we have actually 3 different combinations of possible transient operations, depending on whether we're passing a transient vector on the left side, on the right side, or on both. But one of the things that we show in the paper is that actually you can define a concatenation algorithm that actually think it could be extended to a lot of tree-based meld operations or confluent operations that you can simply use to define transient concatenation for the 3 cases. So if we go back to our original question, can we implement persistent data structures in a systems language? I believe so. I think at least the vector example that we use here, it was the case. And what we saw is that actual performance is quite good. Of course, on memory-intensive operations, having a garbage collector and a garbage collector like the JVM might be an advantage, but the user controls the trade-offs via policies, and we can see that actually in quite of the policy combinations, these persistent vectors can outperform almost any other implementation. And what we also see is that embedding and transients are really effective. In fact, internal iteration and batches of pushbacks, like the one shown before, are similar in performance to the one of a standard mutable vector. And this is great, right? Like this is, I mean, the reason C++ developers use vectors is because of this. So I hope this helps convince them that in these places where they need to achieve this extra bit of performance, they could. Also, we wrote Python and Gal bindings for our implementation. And the Python bindings, we actually benchmarked against another Python library that implements only the regular vectors. And this other Python library is actually written in C, using the Python APIs directly. And we saw that our implementation is still slightly faster than theirs. That kind of shows that this policy-based design actually didn't add any overhead. But the important question is this practical, right? And we did write a text editor, actually, to show how to use this in practice, also to kind of educate C++ developers into how to implement a purely functional architecture in a C++ application. And this text editor actually is able to edit files as large as 1 GB in my machine. And you can copy-paste the whole file in the middle instantaneously, right? And undo is just, you know, the history of previous states. So this kind of shows that actually this confluently persistent data structure is actually quite useful in practice, especially for interactive applications where you're editing this document back and forth. And it performs good for lots of applications. This is all I have to say. Thank you very much.